All right, welcome everyone to another DeveloperWorks Live coding event. I'm Scott Lanningham, a producer with DeveloperWorks TV, and today we're going to learn how to code a machine learning flow from scratch using the new DataFrames-based SparkML. The data used in this event will be from a recent Kaggle competition. Before we meet our speaker, just a little bit of housekeeping. After the event, you'll receive an email with a link to a landing page where you can see the replay of this event, and there'll be resource links for items surrounding what you'll be hearing about today, so you can get into it yourself. You can also leave comments there and interact with us, with our speaker, with each other. If you want that link now, it will be ibm.biz/DWLive010. But again, we will be sending it to you in an email as soon as the event is over with today. If you have any questions for our speaker during his presentation, please use the Q&A feature. You'll find that if you mouse over the player, it should be at the top of the screen. There's a chat feature as well, and you can use that to interact among yourselves if you like. But if you want to ask any questions of our speaker, please use the Q&A feature. We'll field those to him as they seem appropriate within his presentation, and if they seem like something that should be a follow-up at the end, we'll be sure to ask him at the end. So let's meet our speaker. It's Romeo Kinsler, Senior Data Scientist and Deep Learning and AI Engineer for IBM Watson IoT, and an IBM Certified Senior Architect. Romeo helps global clients solve their data analysis challenges. And he is also the host of Discovering Data Science, a series right here on DeveloperWorks TV. If you haven't seen that, you should definitely check that out. Romeo, how you doing?
I'm fine, thanks.
So glad to have you with us. Now, before you kick it off, a couple of questions for you. One, could you tell people what the Kaggle competition is?
Of course. So the Kaggle competition is a website where basically everybody, most likely entities, are publishing their data science challenges, and often there is a prize, so it can go up to $100,000, and you are competing with around 2,000 to 5,000 teams, and then basically there is a leaderboard, and it depends how good you are doing. The better you are doing, the more up you are on the leaderboard, and normally the first top 3, they get the prize.
Okay. All right, cool. And also, before you get into the demo, I wonder if you could give us some history on this new, DataFrames API in Spark. Tell us what's going on there.
Okay, so actually, for those who know Apache Spark, it was all around the RDD API, which is a distributed some sort of array or collection. And on top of this RDD, you had to write relatively complex functional programming calls for your data flow. So what now happened is in Apache Spark, in the new version, there is a DataFrames and a dataset API, which basically resembles to something like a relational API, which you have in SQL databases. And also you can write pure SQL against those datasets. And behind the scenes, there's an optimizer. So it will optimize your SQL code and create calls to this famous RDD API, which most likely is far better as you would have implemented it yourself. You can see it something like a high-level programming language on top of a low level, where RDD is some sort of assembler language, and the DataFrames API is some sort of high-level SQL language.
All right. Oh, terrific. Thank you for that setup. And now the floor is yours. Go ahead and take it away, and we're going to sit back and enjoy your presentation.
Okay, thanks a lot. So can you see my screen?
Yes, I can.
Awesome. So I know this is a live coding session, but I just want to make sure that everybody's on the same page. Therefore, I've prepared. So do you still see the full screen?
We're seeing the side-by-side, slide on the left, small slide on the right.
Okay,
and
okay.
counter.
I think no time to fix that. No worries. I think you can still...
We can read it.
Okay, awesome. So Apache Spark, for those who never have heard about it, just 3 minutes. If you are on a single machine, you have a single process. If you are lucky, you have a multi-threaded implementation, and then you can make use of all your cores. But even in some cases, like using R default packages, you are only running on one single core. Therefore, you have to somehow parallelize your execution. Therefore, the idea of Apache Spark is that you have a single JVM, Java Virtual Machine, which is the driver, and then you have compute nodes. And the execution, so the data processing takes part on the compute nodes, so it's a distributed environment. If you have a single node, you span up multiple JVMs, one per each core, for example, or one for each hyperthread. But then you can even use multiple nodes, but to you, it looks like you are working on a single machine. So that's the idea of Apache Spark in just 1 minute.
Okay.
Then there's the question about storage. So at the moment, everybody is going for a different or separate storage engine, which we are also using in our case. In our case, it is an object store based on OpenStack Swift. So it's an open source, open standards thing. That means you have some sort of a switching fabric, a very high throughput network component between the executor JVMs and your storage. If you have the rare case that you need a lot of I/O throughput, then you can still use HDFS, or in the IBM case, even GPFS. It's a commercial version of HDFS, which is slightly faster. And the idea is you partition your files, and that's happening automatically. So you are accessing a virtual file, which is distributed among all the disks. And the thing here is the disks are directly attached to the nodes. And that means you get the aggregated bandwidth of all individual disks. And that's a really, really fast thing. And last but not least, the RDD is the central first-class citizen of Apache Spark until now. So this is a core element of Apache Spark. It's called Resilient Distributed Data Set. For the Java programmers here, it's something like a collection. For the others, it's some sort like an array. But the thing is, normally a Java collection or an array is kept on the main memory of your node, and the RDD is distributed on all the nodes, either in the aggregated main memory of all the nodes, or even if that is not enough, it can automatically and transparently spill to disk. Okay, so that's the core element. And let me just give you a little overview. There are 4 languages supported in Apache Spark. It is Scala, Java, R, Python, and I have created a little overview, so you can maybe check out the recording afterwards. But in this case, we are going for Python, but I have also the same implementation which we are using today as a Scala notebook. So those are, in my opinion, the most prominent languages. And now the question is, how do you parallelize execution on Apache Spark? On the RDD API, as I've already told you, you have to use functional programming. Functional programming, not to be confused with procedural programming. A functional programming language basically has the idea that a function is the first-class citizen, like a normal variable or a constant. And such a function you can basically use and send to your data. So this is called apply. That means you apply your function to the data set. And in contrast, normally you would iterate over a collection or a list and just increment each element by 1. But in functional programming, you are sending the function to your data. And then the result, of course, is the same list, but incremented by 1. So if you want to parallelize things, then you can use the same data, but partition the data set into multiple chunks and put these chunks to different compute cluster nodes. And then what you can do is you send the function to all your nodes, and those are then executed in parallel. So that's the idea how functional programming works and how it is used in Apache Spark. So this is pretty complicated. So therefore, there exists another thing which is called Apache Spark SQL. And that's really cool because now you can use your already existing SQL skills. So Apache Spark SQL is compliant to ANSI SQL 2003. And you still have the RDD, but then the RDD is wrapped with a data frame, and you have a relational API on top of it, and also an SQL API. And you can also mix and match those two. So you can write relational Python or Scala or Java or R code, And you can also implement things in SQL, and you can join and mix and match. And also for real-time computing, there is the new structured streaming API, and even that has the same API. So it's pretty cool. And for the Scala and for the Java users, there is something even more performant. This is called a data set. It uses the typed nature of those programming languages to even improve speed. So there are two components in this Apache Spark SQL. One is called Catalyst, which is an optimizer, which you also find in relational databases, which basically optimizes execution plans and creates calls on the RDD API for you, which normally is even better than you could do it. And the second thing is even more interesting. It's called Product Tungsten, which is taking away memory management from the JVM, from a Java virtual machine, and does memory management on its own. And since Apache Spark 2.0, we have something called whole stage code generation. So basically what this means is it implements Java bytecode to implement your data processing flow. So there are no unnecessary loops and function calls anymore. So it's like you would implement something like assembler. Pretty cool. Enough slides. So let's directly dive into the demonstration and the live coding. So we will start with datascience.ibm.com. The tool is called IBM Data Science Experience. You can sign up for a trial, and there will be a free tier soon, if I'm not wrong. So Data Science Experience is in its core something like Jupyter Notebooks and an Apache Spark as a service. There are multiple components in addition, like IBM Watson machine learning, but I don't cover those today. So what I do is I will create a new notebook. So this is now a Jupyter Notebook, which I'm creating. I'm calling it EW Live. I select Python 2, which is Python 2.7 as programming language. I select Spark version 2.1. Very soon there will be Spark version 2.2 as well. And I create a notebook. So what now happens in the background is that this notebook gets started. And for those who know Jupyter, every notebook is associated with a so-called kernel. A kernel is the interface between a notebook and a programming language. And now the Python kernel is started. And this Python kernel is now accessing an Apache Spark cluster. And on the first access, the Apache Spark cluster will be provisioned for you. So that's a private Apache Spark cluster running on top of Kubernetes and Docker, which is only there for you, okay? So I have two notebooks now. One is called ETL, which shows you how to get the data from the Kaggle competition and ingest it into the object store. If you have time, I will walk you through that as well. But I have already provisioned the object store with those files. So let me just show you one thing. If you search for Bosch and Kaggle, you will land on the competition or on a challenge website. So this basically tries to explain what you need to do. But as usual, in my experience, if you are a data scientist, you get data from somewhere. It's a pile of shit. And this pile of shit, it's normally like the people who give you the data, they vomit on top of it, some documentation. So what you get is normally really bad quality data, bad quality documentation. And also in this example, this is the case. But at least we see here we have a couple of files. So those are zip files. It's a CSV file, and this is zipped. So it is really small if it is a zip file, but if you extract it, it gets quite large. For example, I think that train numeric.csv.zip is now 270 megabyte, but if you unzip it, it's more than 2 GB. Anyway, that's not a problem because you can download it, extract it, and put it to the object store using Apache Spark completely in the cloud. So, as I said, if you have time, I walk you through. Otherwise, I just share the notebook with you. But now we will actually just start coding. So here on the right-hand side, you see all the files in the object store. And in order to read that from the object store, we have to insert some code. This is done automatically. So what this basically is doing, it sets up some environment variables, how to access this object store, and it creates a path for you. So let's run those two cells. And if I just print out this path, you see here, it's a relatively complex path, but it's just an URL. So we basically don't care. You see here the type of the source is also Swift 2D, which is because we are using OpenStack Swift as an object store. Otherwise, we would have FTP or HTTP or file or HDFS as a prefix. Anyway, what we do now is we create a data frame. So we call this numeric, and then we say Spark dot read, and then we say the type of file we want to read. It's a so-called Parquet file. And the thing with Parquet is it's a special file format for big data processing, which compresses data, and it's a column store, and it somehow acts like a database for you. So Apache Spark together with Parquet files have some properties of analytics database. So this is pretty cool. So let me double check which one I have to use here. So this one is path 2. I have a little cheat sheet, which you are not seeing. So path 1 is numeric, and that's this one. Where's my mouse? Here's my mouse. So this one, path 2. And I'm just running this. So that's basically all. This will create a data frame for me. So I see here, that's the progress. So this actually is the Apache Spark job now running on the cluster in the background. Whenever you see a star here, that means that something is running in the background. And if you have a number here, that's the task ID, which has been completed. So let's do the same for the second data set. So if we maybe go back to the competition website, you see here there is a categorical, numeric, and date data set. So what those guys have been doing is they just exported data from their production systems, and they somehow anonymized it. So you don't see the actual column values of their system. They have just used IDs for their columns. And you have one file for categorical data, one file for numeric data, and one file for timestamps. In this example, I'm just ignoring the timestamps. I'm only taking into account some categorical and some numeric data, okay? So let's actually load the other file. So this is done. Okay. Let me just double check whether I have now named those correctly. So this ABF6 is path 1. And now comes categorical. And here in my cheat sheet, ABF6 is path 2. Yeah, I think I've chosen the correct files. And now my mouse is gone again. Here's my mouse. Okay, so what I have to do now is I have to, so let me first show you what the contents are, okay? What we can do is we can say numeric, so df numeric dot print schema, and shift enter runs the cell. So you see here, those are the contents. So we have one ID, which we don't need. That's basically the ID of the product the production line has created. Then we have this anonymized field names here. You see there are a lot of those, and I'm only taking into account some. And then you see response. So response is the thing we want to predict. It's either 0 if the part is broken, or 1 if the part is not broken. So we have to predict whether the part is broken or not based on all those data points. And let's do the same for categorical. And you see as well a lot of fields. And again, at the bottom, you see it's still not fitting inside this window, so it's a response as well. So now what we do is we have a look at one item, or we can also have a look at the first 20 items by calling show. So this will trigger Apache Spark job, because now all the execution is executed on the Apache Spark cluster. So, and since there are so many fields, it's a bit hard to read, but what you see is there are some data points and also a lot of null values, but also some strings, because this is, as I said, categorical data, okay? So now let's actually do the following. Let's actually use some SQL, okay? So in order to use SQL, you say create or replace temp view, and we call this temp view dfcat. Okay, so now we have registered this data frame as a table dfcat, and now we can say Spark SQL, and we can write plain SQL against this data frame. So we select ID, and then we select L0, S22, F545 from dfcat. Okay, and we just assign this a new name, because the execution of a SQL statement, again, is a data frame. So notice how fast this was. So actually, we didn't execute any SQL so far. So all the executions in Apache Spark are lazy. Data is only read from the underlying storage if it is needed. And we have to do the same for the numeric. But before we do that, we have to register numeric, and we say create or replace temp view dfnum, and again we run an SQL statement, and in this case it's dfnum, and what we need is ID, but now we need different fields. So we take the L0, S0, F0 field, and then we take just two other fields. So then we take the F2, and we take the F4. So note we are, and then also the response. So note we are not getting the response in the first statement, because those are matching. That means we are now, or later, we are joining those two data sources, and then we have basically the response from the second one. So let's actually see if that works. No, there's a typo. Okay, this seems to work. And now it's a bit more complicated. So what we will do now is we have to do some pre-processing. That's always the case. If you're doing data science, 90% of your work is pre-processing. So we say dfcat, and now we are using the relational API. So we could have written an SQL statement, but we can say join dfcat with dfnum. So out of the box, this is inner join, and join on the ID column. And then we use df to create or replace temp view. So the result of the join we will access using SQL. And now some more SQL. We want to get rid of null values. So we rename that and say spark.sql. And now a feature of those notebooks I love, you can inline strings like that. If you have 3 double quotes, everything what you write here is basically one string. So you can have line feeds in that string. And what we do is we select, and then we select a couple of things. We select response as label. So data scientists call their target variable often label. And in case when where's this one? just copy that. If this one is null, then we say NA. Okay, so that's some NA treatment. In case this field is an empty string, then we say NA. I don't think we need a comma here. And else, we say this one should just be copied into the same one. Okay, comma. So that's the case for the categorical field. And we have to do the same for the 3 numeric fields, okay? So just in case this field here is null, then we say it's 0.0. And else, we say and s. Okay, so now I copy this to other times. So let me fix the layout. So we are not inside Python anymore, so we don't have to take care of the layout too much, but still it's a good practice. So now I have to use F2 here as name and F4. So those are the labels I'm using. So, and then finally we have to specify from where we are selecting. It's from df. Let's see if that compiles. Of course not. Let me check where the problem is. So there's a comma, there's a comma, there's a comma. This is fine. There's a comma, select, blah, 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 from df. So this seems to be all correct. Let's see what it says. It seems to be correct. Luckily, I have a cheat sheet. So let's just double check whether the cheat sheet works. If the cheat sheet doesn't work, then I've messed up the file names, but no problem with that. I will fix that. Okay, that seems to be better. Okay, so what we now have done is we have created a SQL script which gets rid of all the null values. Now we can actually start with machine learning. So for those of you who are familiar with the traditional SparkML lib, it's completely different because we can now run on top of data frames instead of running on top of RDDs, which is pretty cool. And since we are in Python, we have to import some Python classes for machine learning. So it's PySpark.ml. And the first thing what we are doing is we are doing some feature extraction. So we have to transform our categorical values a bit and also our numerical in order that Apache Spark ML understands it. And one is a so-called one-hot encoder. So one-hot encoder is very important in machine learning. A one-hot encoder transforms one column with multiple different categorical values into multiple columns in the following way. So let's assume you have one column with 4 different possible values. This one-hot encoder transforms this column into 4 columns, and the values are only 0 and 1, and only that column which contains the actual value, this has a 1. So only one of those fields can be 1. So that's a very important thing. And the second tool we need here is the string indexer. Because remember, we had some strings in the categorical file, like T1, T4, T5, whatever that means. And we have to transform those into categories, into numerical categories. So we call this an indexer. And we create a new string indexer. For the Java programmers in here, or the Scala programmers, you would use new. But here in Python, you can directly call a constructor. And Python is doing nothing else than wrapping the JVM stuff for you. So it's basically like you are programming in Java. and you have to specify the input column. And the input column of this string indexer, of course, is our categorical one. So this is this one. And then you have to tell the system how the output column should be called. And we call it the same, just we append index, because now it's indexed. And let's try to run it. So we have index equals indexer. So this indexer has a couple of properties. The most important is set handle invalid. So the thing is, it might contain values in the index which are not currently present, and those we want to skip. So the central function here is fit. So you are maybe asking why it is called fit, because you might know fit from a machine learning model. But as I said, a string indexer needs to keep state, needs to keep track of all the already seen labels. And therefore, all the components in Apache Spark ML which have state have a fit method, okay? So we are using this df not null data frame as input to fit. And then this basically creates only the table between the category strings and the indexes. And then we say transform. And then we should get an indexed version of this data. Let's have a look. And basically, this means it only creates an additional column which represents the transformation which we have been doing. You see, it's a bit more complicated. It's a two-stage process. The first stage creates the index internally, and the second stage actually transforms. So let's have a look at indexed, and let's say show the first 20 rows. Okay, so you see here, we have now an additional column, which is called index. So you see it's 0 most of the times, but let's actually do one thing. So, or two things. So the first thing, we can get the first column, and we can directly access this column. All I'm doing is running on Apache Spark on the cluster in the background. And this is pretty cool, because now, in contrast to Python pandas or R, you are not limited to the dataset size. You can execute this on 1 megabyte or 1 petabyte. I don't care. So the code doesn't change. So you see here, this is, if we say type, I've not tried this before, but most likely, if we check out the type of this, it should give you vector. No, it's a float. Okay. Let's go to this later. So, and the other thing, what I can do is I can say distinct, and then you get the different values, and you should see only a couple of those. But anyway, this is the first thing. Now what we have to do is we have to use the one hot encoder. So this is encoder equals one hot encoder. And again, we are calling the constructor. And the input column now is this one. Because now we have already transformed the string labels into numbers, but we have still many different numbers. Maybe I just show you that. Let me double check. It's pretty important that you get the idea. So we have now select this column we have just created. So that's like you would do it in SQL, and then we say distinct and then show, of course, because we're getting back a data frame. So now that I wanted to show you. So you see here, those are the distinct categories. So you see 1, 2, 3, 4, 5, 6. I'm lazy. So pretty cool. So count.
Romeo, can I ask you a question?
Of course.
Someone asked that they said, I'm confused. They said, is the difference between one hot and regular label encoding that one hot doesn't give value to that category? Is that they're trying to understand that?
So in one hot encoding, you don't give a value, because maybe it's, I don't know the other one, but most likely it's a two-stage process I'm doing here, because first one is the string indexer, which transforms the category strings into numeric values. And the second, the one hot encoder, transforms the single column multiple values, which we have seen before, into, in this case, 14 distinct columns, where only one of those is one. But in order to answer your questions, I have to check what the algorithm is called. So let me, I do the following. I watch the recording, I see what your question was, and I will answer that in the comments of the recording. Is that a deal?
Okay.
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 So you see here 14 different values we have here. And so let's use this as input column. And then we set output column, and we call this basically vec. And then, so that's only the definition, and then we say encoded equals encoder, and then now we use transform. And the reason why we don't use fit here, because one hot encoding doesn't need internal state. The only thing what this guy is doing is it's calling a distinct in order to get all the different codes, and then it creates internally 14 columns, and then basically does this transformation. So this transformation doesn't need any state, therefore it's called transform instead of fit. So we are using the data from before indexed, and we just run this.
Yeah, the participant said thank you. That did answer the question. So
is it? Okay. Yeah. But let me still double check if I answered it correctly. So the encoder. So we have encoded this now, and then we say encoded print schema. So you see here we have now created an additional column which is called vec, and we still get the first one here. And then we use this as column name. That I wanted to show you. So the type of this column is now not string or double, it is called sparse vector, and sparse vector is Apache Spark ML data type. And this Apache Spark ML data type is called sparse vector, in contrast to a dense vector. So a dense vector with 14 elements would consume, of course, 14 elements of space. But in this case, this sparse vector representation has the same semantic power, but uses much less space. Because since we know it's a one-hot encoding, only one of those 14 slots can be one. And here it says, okay, this is a sparse vector of length 14. So it's actually 13, it starts from 0. And then it says, okay, element number 0 is 1, and all the rest is 0. So that's a very compressed representation which SparkML is using. Okay, what next? So we have this encoded, and now actually what we have to do is, before we can feed that into a machine learning algorithm, we have to use the so-called vector assembler. Okay, that again transforms all our columns in one very dense and compressed sparse vector representation, and that's something which we will implement now. So the first thing, we have to do some imports. So it's PySpark ML. We import pipeline, more on that later. Then, because actually we are creating a pipeline, therefore we have, of course, to import it once. So Spark ML lin elk. So we import the vector object, which we will need later. And from PySpark ML feature, we import the vector assembler, which we are using in a second. So now we create an array, transformers, and that's basically the array which we are using later, because all those are stages in our process. So the first one is indexer, if you remember. The second one is encoder. And the third one we are just creating inline here. It's a new vec vector assembler. Okay, so we are calling the constructor on this, and then we say set input columns, and now we have to pass an array of all the columns we want to assemble. So the first one we want to use is, of course, that one hot encoded vector. So we are assembling a vector into another vector. It will be a huge sparse vector, which actually is the input for our machine learning algorithm. Then the second is, of course, our 3 numeric columns. So put that here. And then we set output columns, and then we have to give it a name, of course, and that's called features. Always it's called features in machine learning, okay? So that's basically all, and of course it's not working, cannot import name pipeline, of course, because there's an E missing. And then no module name features, feature. And then vector assembler, and then program here. And then set of course, it's output column, not output columns. So this is working, at least the definition. And then let's actually execute it. So we create a pipeline. Now it's getting interesting. Pipeline. So we are calling the constructor again. We said set stages, and set stages actually expects an array of transformers, which we have created just before. And then, of course, we call fit. And then we use our original data frame, because now all those stages are basically executed subsequently. And as I said, it's always a 2-stage process. The fit basically just populates the internal state representation of all the transformers. And then we say transformed equals pipeline dot transform. So this is actually transforming. So the first call is only preparing, kind of. And you see again, it's very fast. So the 33 task was taking a bit of time, because in the background, all the transformers have been populated with internal state. But this one is just a definition. It's not running until we use the transform data frame. Okay, let's give you an idea. So this should return, see here, it's a data frame. Okay, transformed is again a data frame. So now we have most of the things in place. What we can do is we can, of course, print a schema to have a look what happened. And it's always a good idea. So now we have features, okay? And again, we can say, for example, first features. Again, we have a sparse vector, and let me just explain you this. So we had initially a vector containing only the categorical 1 hot encoded columns. Now we have added 3 additional. First we had 14, now we have 17. And again, we have the first element of the vector is 1. The next 13 elements are 0. Element number 14 is 0.03, element number 15 is minus 0.034, and element number 16 is minus 0.197. Okay, so this is a 17 element vector, but since it's using this sparse representation, you have only 1, 2, 3, 4 elements. Okay, so this is now the transformed data frame, and now we are doing machine learning. Okay, so what we do is we import from PySpark.ml classification, because remember the Kaggle challenge is a classification problem, a binary classification problem. And we import random forest classifier. Normally, I'm not using random forest classifiers anymore just for sake of execution speed. What I normally use if I'm not using neural networks, by the way, in about 4 weeks, I'm giving a presentation on deep learning, how to use deep learning on Apache Spark for outperforming all the state-of-the-art algorithms. But if I'm not using neural networks, I'm using a gradient boosted trees. But anyway, let's use this random forest classifier now. So the import is correct. And our random forest classifier is a random forest classifier. So we call the constructor. And then what we do is we set label column. Label column is called label. So we remember, we have renamed the response column to label before. So what we get from Bosch and Kaggle is response, but we renamed it as label. So we can refer to it here as label. Label. And yeah, I think that's correct. And then we have to set features column. And note, it's not called features columns. It's called features column because it expects that we have used the vector assembler stage in order to create one column containing a sparse vector out of all the columns we want to make use of. So we call those features. If you don't remember where this comes from, we are doing it here. You see here, vector assembler, we are using those 4 columns and we create one single column containing only sparse vector objects, and we call that column features. So let me see, that's basically all here, and it's of course not working. What's the problem? Random set label column. Okay, so label column, and now we can execute it. So if we want to obtain the model, we have to say pipeline, and then we set stages, and then it expects multiple stages, but we have already transformed the data, so we just skip those stages and directly only create an array of one single stage, which is called RF. Otherwise, you could, for example, use indexer and encoder and assembler as additional stages, but this is not necessary because we are now feeding directly into this model, this transformed data frame. Okay, so then we will obtain a model. And again, this is a 2-stage process. So we are first preparing the model object, and then we can use the model object in order to say transform. And we use the transform data frame again. And we want to store this into a result variable. So you see, whenever this star is disappearing and the number comes, we know the job is finished. So let's give this a couple of seconds. Okay, 42. 42, by the way, is the answer to all questions. You know that? So now we actually execute this. Okay, so now we have the result. And now normally what you do is, if you are not using such a pipelined environment, you have to check how good you are doing by comparing the predicted values. So let me just show you. If we say result print schema, you see here there is a raw prediction and a prediction. So that's basically coming from the random forest classifier already. Let's have a look at the first row. If you want to have it a bit more nicely, you can either use show, or you import Pixie Dust, which is an IBM visualization library, but it's open source, so anybody can use it. And if you are not in an IBM environment, you can just say pip install Pixie Dust. This will also work, but in this case, we don't need it. And then what we say is we say display result. Oh, better copy paste. And this is pretty awesome because now you have a table view, but you also can draw charts, and it runs on top of the DataFrame API. So that means if you have 1 petabyte in a data frame and you display it with Pixie Dust, there's no problem. Now you see here the contents of this result. So the label, the features, the raw prediction, and the prediction, and you see also the probability. How certain is the algorithm that this prediction is correct? And maybe you know this from the IBM Watson system, or in any machine learning or deep learning environment, you always get a certainty how sure you are that you are predicting the correct thing. So this we will have here. So now it's time to evaluate. Okay. Normally, as I said, what you normally would do is you check this prediction and you compare this prediction against the label, and then you basically count how often did you do the correct job and how often not. But in SparkML, this is far more simple. So we import spark.ml evaluation, and we have different evaluators for different tasks. So we say for this binary classification task, we take the binary classification evaluator. Okay, and then it's pretty simple. All what needs to be done is we say evaluator equals, of course, we call the constructor of this object, and then this constructor has a parameter. It is called prediction call. So what it expects, we have to specify the raw prediction column of the model. So it's called raw prediction. So this is our evaluator, and again we say evaluation equals evaluator dot evaluate, and then we just simply pass the result. Again, a Spark job gets triggered. Okay, let's see what evaluation is. So we see here we have 0.54, okay? And let's check out the leaderboard of the Kaggle competition, and you see here the top performer was 0.524. So we outperformed this guy. But maybe if you know why, just put it into the chat window. Let's see if somebody knows why this is the case. And I'm done with the first part. So Scott, if there are questions, we can answer them now. And if not, I can show you how to ingest data directly from the Kaggle database.
I've got a couple of questions for the end. I don't know if you'd like to take those now, or if they're more general questions. We could just do them at the end if you want to.
Okay, no, let's take them, because then the people who don't want to see how I'm doing the data ingest, they can just
Okay. Okay, so here's a general one that came early on. What are some of your key evaluation criteria for data for a machine learning model so you can weed out the POS?
Oh, I have to skip that. Let me read about that and answer that in the recording. Okay, next one, please.
So how about, there were two others. Can you fix some data by the way you prepare it for the ML model?
What you mean by, maybe can you post in the chat window what you mean by fix? Okay, then I can take this. Yeah.
Okay. And then the third one is, how again does using RDD and data frames differ? What difference does this make in ML modeling?
Oh, okay. Yeah, it decides whether you are using MLlib, which is a RDD-based API, or whether you are using SparkML. That's the DataFrame-based API. The latest news I have is that MLlib is now being deprecated. So MLlib still has more algorithms implemented, but over the next couple of months, definitely SparkML will have re-implementations of all those. So you can basically forget about MLlib as soon as you don't need an algorithm which is only present in MLlib and not in SparkML. And the pure advantage of that is if you are using the DataFrame API, you get better performance. So you see, I was always using Java and Scala with Apache Spark for performance reasons. But now, since we are only expressing the data execution graph using Python, there is no issue in using Python because it gives you the same performance, because the engine itself will all run on top of Scala and JVM code.
Okay. And here's some clarification on one of those questions. He rephrased it. He said, how can you make some data more valuable to the ML model by the way you prepare it? That's what he was implying.
Okay. Yeah, so those are the, let's say, state-of-the-art things you're doing. So the best thing of what you always have to do is you have to do this string indexing, you have to do the one-hot encoding. Another thing what you often do with numerical data is normalization. So for example, if you have some columns with value ranges between 0.25 and 0.75 and some others with ranges between -600 and +600, it's definitely a good idea to normalize the data. And what I always do is I just check the NA count. So I'm checking how many items in this column are 0 or not usable. And another thing what I'm doing is sometimes I'm running a correlation algorithm, so I can basically get a cross correlation of all the columns, and that gives me some sort of an idea how much information such a column contains. And if you stick into this series, I think in 8 weeks I will show you something about deep learning and a method how you can create more data from a limited data source. Okay, this is a deep learning neural network, and I will just explain how this works.
And
okay.
you say you'll be talking about that on the Discovering Data Science series?
Yeah, I'm planning to create another live coding session as well.
Oh, great!
Anyway, all I'm doing is ending up in my data science series YouTube channel, so you can always check it out. Yes.
All right. So go ahead if you wanted to finish up then.
Okay. So one thing I've promised in the description is how to do ETL. And let me just try to do that from scratch. So if you are on the Kaggle site and you click on data and you click on download and you are not logged in, then what basically happens is that you have to log in. So your login is stored in cookies, and I'm here talking about small data sets, but in bigger data sets you might get into trouble. Therefore, it's a good idea to not download all the data to your local machine, but just do everything in the cloud, okay? But maybe for sake of time, because there's only 1 minute left, let me just show you what I've done in order to obtain this data. So the idea is that everything runs in the cloud without any network problems, because the cloud systems, they have really, really big wires, and therefore I can use an Apache Spark notebook for doing ETL. Okay? ETL stands for extract, transform, load. And one cool thing in this data science experience tool, let me scroll down here, is so I can always issue Unix command lines here with an exclamation mark. So you see here we have a staging area, and this staging area is at the moment nearly 1/4 of a petabyte, and currently we have 38 terabyte free space, and you can use the staging area for doing whatever you like. So in this case, what I had to do is, in order to download the zip file, I've just used wget. And since I have to log in, what I've done is I've exported all the Kaggle cookies And again, here, this is the Python way of doing it. It also works in Scala to create one string. And then what I've done is I've just written those cookies to a file. And now I can basically download this zip file directly from Kaggle with my login credentials using this cookie file. Then I can also unzip it. So I don't care if this file is afterwards 10 GB or 100 GB or even up to 35 terabyte. I don't care. And even I don't care in ingesting the data again into an object store, because CSV is a pretty bad file format. So what you can do is you just read it. So that's the way to read a CSV file in Spark. So I have a header and it infers schema. That means if you don't put that option to true, you get string as data type for each column. If you say infer schema, it tries to guess the schema, and in this case it works awesome. So it discovers that data type is double and string for the labels. Then I say repartition. I create only one partition of that file, and then I say write, and I set parquet. And this is the path, the URL for the object store. And in this notebook, I basically just downloaded a huge zip file from Kaggle. I abstracted it, and I created a data frame out of Apache Spark. And then I used Apache Spark to write it as a parquet file into object storage again. And the size of the zip file and the parquet file is basically the same. So I'm some sort of working on top of a zip file, but it's a high-performance column store compressed format. Yeah, that's basically all I wanted to show. I will share those notebooks as well. So maybe some things, if you want to read more, nopanic.ai. I have all those things in my blog. It's a IBM blog. And also more on Apache Spark. I've written a book on mastering Apache Spark. You can also check this out. And yeah, Scott, are there any questions?
Not anymore, Romeo. I think you covered it well.
Awesome.
Great presentation, man. Thank you so much.
Thank you as well, and all the best. Have a nice evening.
Don't go yet. I'm gonna give them a little final goodbye information and thank you again. But if you will release the screen share, then we can get back to the top of the show here. And I just want to remind everybody, you will be getting an email at the end of the broadcast here with a link to ibm.biz/DWLive010. That page will have, in the next hour or two, the replay of this webcast, so you can share it with friends and watch it again yourself if you want to cover some of this again. And there will be resource links to a lot of what Romeo talked about, so you can dig into this yourself. So again, Romeo Kinsler, thank you so much. Great job, and we look forward to the next live coding event. You heard him. He said he's going to be back. There's going to be more.
Thanks a lot.
Just the beginning, right?
Yeah, of course.
Okay, thank you again for watching this. This has been a DeveloperWorks live coding event. I'm Scott Lanningham. Talk to you soon.